Good morning, ladies and gentlemen. Today, we're going to continue our journey with limits, and we're going to talk about something we've mentioned actually in the past called end behavior, also known as infinite limits. That's usually how I refer to them, and also known as limits as x approaches either positive or negative infinity. Now, first thing I need to say is not all infinities are the same. Just want to put that out there. Seems kind of wild. We'll talk about that and do a little bit of that as this goes on. But the first thing I want to do is give you some ground rules as to why everything that I'm about to do in the next couple slides works. And these are called the theorems, these ground rules. So here they are right there. If you wanted to take a second, pause the video, and copy these down. I am going to talk for a brief second about what they are. In the first one, as x goes to positive infinity, k represents a number, just any number. So like the limit as x goes to infinity of 7 equals that number 7. Because if this is a number, think of it like a constant function, whereas you have yourself like a horizontal line somewhere, like maybe down there, let's say. And that maybe is the equation y equals -2. Well, as x goes to positive infinity, the y value is staying at -2. And that's kind of like what that's saying. Or if x is going to negative infinity, it's the same thing. Negative infinity is pretty much the same thing as positive infinity in terms of these theorems and the rules that we're going to do. There's a little bit of differences, and when those differences come up, I'll point it out. Now, the next one is as x goes to infinity of x. So think of the diagonal line, y equals x. As x goes to positive infinity, we're going up to positive infinity, we're going up forever. In a similar way, because as x goes to negative infinity, we're going down forever, so that would be negative infinity. Finally, the last one here, as x goes to infinity of 1 over x, and in case you don't know, we actually graphed 1 over x earlier in the year. Oops, remember these guys when I graph these little hyperbola-looking things? 1 over x looks like this. So as x goes to infinity, 1 over x is getting closer to 0. And we call those things horizontal asymptotes, which is end behavior. And this guy would be basically a slant asymptote, just to let you know. So there's a connection from, I don't know, second quarter, first quarter, something like that. All right. Now, these ground rules we're going to use to be able to evaluate some things like this. Now, it would not be nice for me to say, just plug in the infinity. You can't just say, that's going to be 2 times positive infinity, the 5th power, because how do you evaluate that? It's just big. You can think of it like a concept, though. And also pay attention to the signs. Say if things that are positive become negative or vice versa. But if you're looking at this, 2x to the 5th, well, let's say infinity to the 5th power is just a bigger infinity. So, yeah, you could argue that this is going to positive infinity, and that would be correct. Now, however, if I'm doing negative infinity, what's this guy going to? Now, you might want to jump the gun and say, then clearly this guy's going to negative infinity. Now, because you're squaring the x there. If I'm squaring, and if I have negative infinity thrown into there, won't that become positive? And then if I'm take infinity and multiply it by 3, won't that still be infinity? So the answer is positive infinity. Okay, now things are going to get a little bit different. Because now I've got a negative infinity here, and if I put that negative infinity into x to the 5th, if I take a negative thing and raise it to an odd power, it remains negative. 2 times that negative then still is negative. So you have to pay attention to the signs and see what's going on. Okay, lastly, looking at this guy. Now we got 3 terms, a polynomial, something much bigger other than these single monomials going on. However, I do want to point out, when you're taking infinity and raising it to the 3rd power and the 2nd power, these guys become irrelevant. They're too small. They don't really matter. What matters is the term with the highest degree, because that's x to the third. That's going to be like the dominating term of this. Then just apply the rules like we did up here. So let's see, we're going negative infinity. We're going to cube it. It's still negative. Multiply it by 6. It's still negative. Negative infinity. And I just want to point out, before anybody ever says negative 6 infinity, if you ever write that down, I'm going to call you a bad word. I don't know what that word will be. Maybe like silly head. But I'm going to say it. You don't do it. It's negative infinity. Moving on, because these are too easy, right? Boop, let's kick it up a notch. Oh, yeah. Rational functions. So x is going to positive infinity. And we actually dealt with this earlier in the year when we talked about things like horizontal asymptotes. And I said if the powers are the same, like they are here, you ignore everything other than those powers. So like the -5 and the +7 are irrelevant compared to infinity. So you're looking at 3 over 6, right? Because of the same power, you're allowed to do this. Wait a second. 3 over 6? Don't you mean 1/2? Oh, yes. We mean 1/2. Let's move on. Looky here. All right, positive infinity again. Irrelevant terms there and there. So now we're looking, imagine 2x squared over 17x to the third. Well, let me simplify that a little bit here. That's like saying 2 over 17x. Now you see how the x is on the bottom? If you remember, there was a trick to that when we did this, and that was that it equals 0. Because the denominator is going to get super huge. 2 over infinity going to 0. I just want to jump back for a second. That's like saying this guy right here. Just so you understand. 2 times 1 over x. As x is going to infinity. So if you have more x's in the denominator for free, you're learning that it's going to 0. Here we go. Now the powers are the same. So we could ignore all the little stuff and just look at it like that. 8 over 12. Because the x to the fourths are going to cancel because they're the same infinities. And wait a second, 8 over 12. Isn't that like 2 over 3? 2 thirds. There we go. That was the end of this. All right. Boop. Oh, yeah. Now with roots, you got to be careful where the roots are. All right. So because of the way that the root is going over the whole rational function, I can kind of put that root on pause. Just deal with what's going on in here first. All right. So the 38 and the 1, they don't matter. Irrelevant. It's x squared. So, okay, they're going to go away with each other. And you're just left with 4/5. Now we can bring the root back into this. So it's just going to be the cube root of 4/5. In case you couldn't tell, the cube root was going over the whole function, by the way. So where the root is actually important. Because if it's not going over the whole function, like only just part of it, you got to be careful. Now, x is going to negative infinity. I purposely gave you this one here. It's a little tricky, so pay attention. Again, the rules apply. They're not going to matter too much. You can ignore that. So it's like we're looking at the square root of x squared over 3x. Now, a lot of people want to jump the gun and say, oh, the square root of x squared, that equals x. And I'd be like, no, that isn't correct. The square root of x squared technically equals the absolute value of x. You have to be careful of that concept right there. So, now let's look at this. Let's fix that up. So it's like saying the absolute value of x over 3x. Now let's take our limit again. Let's look at this because we had a negative infinity here. Are these powers the same? Yes, they are. They're both to the first power. So are they kind of canceling each other out? Yeah, they're kind of canceling each other out. However, let's pay attention to the sign of the whole thing. Because this guy is negative, that'll be a positive up there, and this will be negative down here. So we're going to get negative 1/3. Now, you got to be careful of those negative infinities, and be careful of things like the square root of x squared. Lastly, one other kind of example I want to look at, similar to what we had to do a couple days ago here. Now, if I put the infinity in here, you get infinity to the 6th power plus 5, and then, people want to say, that's like saying, the 5's not going to matter, and isn't this going to be 0? Not necessarily. You see, the problem is you don't know if these infinities are the same here at this point, or if something else is going on inside of that square root that's going to make everything not work out the way you want it to. So what we're going to have to do is we're going to have to go back to using the conjugate to kind of figure things out properly. So you might be saying, the conjugate, what are you talking about? I don't see a fraction here. That was, hold on there, sunshine. Because we could put that guy over 1, and that gives us the ability to do the conjugate. X to the 6th plus 5 plus x to the 3rd, top and bottom. This is getting kind of gnarly looking here for a second, but it's going to be okay. When I multiply the top there, I'll get the x to the 6th plus 5 minus x to the 6th. And down below, x to the 6th plus 5 plus x to the 3rd. So now we could say, hacha, those guys are going to take each other out. And we could say, all right, look at this. The limit as, what am I doing? That's nothing. Let me get rid of the whole thing. I'll just start over again. There we go. Limit as x goes to a positive infinity of 5 over x to the 6th plus 5 plus x to the 3rd. And yeah, this is, looking at this, you have, this is going to be kind of irrelevant here. So yeah, you could say like x to the 3rd. That's, oops, I messed up again there, people. I mean to do that. Let's get rid of that. There we are. You could say, isn't that saying like x to the 3rd there? It's actually greater than x to the 3rd. So, but that's fine to say. And then you're adding this other x to the 3rd here. And isn't that 2x to the 3rd? So yeah, that makes 2x to the 3rd there. So all right, I got a little distracted here. So we're looking at the limit as x goes to infinity. We have 5 over 2x to the 3rd, and the power is bigger on the bottom, 0. Now, I know what you might be saying. Earlier on, we came up with that 0 thing, but I'm just letting you know it's not always going to be that way. Pay attention to the function, work right, have a nice day, be safe.